Hi everyone, my name is Goo Shu Cheng and I am member 1 of our group. Today I will be presenting phase 1 of our proposed next generation Malaysian e-gate system, which cover the token integration and initial screening layer. So basically my part focus on what happened before any biometric scanning even begin, and I will explain why that step is actually the most critical foundation of the whole system. Let me start with some context of introduction. Malaysia has some of the biggest border checkpoint in Southeast Asia. KLIA proposed around 48 million international passengers in 2019, and the Johor Singapore Causeway handled between 300,000 to 400,000 travelers every single day. Beyond border control, even Malaysia hospitals have faced patient misidentification incidents, which show that variable identity verification is a national issue, not just an airport problem. Now, the current automated clearance gate suffers for three main problems. First, they have a high false rejection rate because fingerprint sensor struggle with warm fingertip and facial recognition fail under mask or poor lining. Second, they only do one-to-one verification and do not check traveler against every criminal will slip in real time. Third, and most critically, biometric matching happens without first verifying whether the travel document is even Guinness. If someone presents a passport with a manipulated chip, the gate could potentially let them through. That's actually what our proposed system aims to fix, starting with phase 1. So phase 1 is about reading the physical token and verifying it cryptographically before any biometric scan takes place. We support two token types. The first one is ICAO 9303 biometric is proposed, which store facial image in DG2. Fingerprint template in DG3 and all data hashed in the document security object. The second is the Malaysian MyCard, where fingerprint matching happens inside the chip itself through on-card mesh, so raw fingerprint never leaves the card. To read this token, the gate use NFC and 13.56 MHz through 4 steps. The reader sends a signal and the token responds with its ID. The reader then selects the RTD application on the chip. The gate camera scans the machine variable zone on the passport to retrieve the season key. Finally, under the encrypted season, the gate retrieves the data group and the document security object. You can see the full flow in figure 1 on the right side of the slide. Once the channel is open, the gate establishes a secret season using either PSC, which use triple DES encryption derived from MRZ data, or PSCE, which use elliptic curve different Hellman and provide stronger forward secrecy. Both protocols prevent chip screaming because the season key requires physical access to the document. After that, passive identification is performed. The gate verifies the document signal certificate and gets the country singing CA from the ICAO public key directory, then rehash every data group to confirm nothing have been tampered with. Any mismatch trigger an immediate alert. Finally, chip authentication is run to detect cloud chip. The cloud chip cannot replicate the private key permanently embedded inside, so it will fail the challenge. Only after all these phase passes does the system issue a sign attestation to the biometric modules. No biometric scanning begins until that attestation is received. Figure 2 on the right shows actually how this trust chain works from the ICAO PKD all the way down to the e-gate verifier. So to summarize my part, phase 1 ensures that every traveler document is cryptographically verified before the system even considers scanning their face or fingerprint. The token is read via NFC. The ICAO PKI chains confirm it genius and untampered, and only then does the sign attestation unlock the biometric phase. Thank you, and that's all for me. I will now hand over to my next group member, which is Jian, to talk about the next phase.
Good day everyone, my name is Lim Zhi Yuan and I will be presenting phase 2 of our proposed next generation Malaysian e-gate system. So phase 2 is focused on the multi-modal biometric capture and the technical challenge we face in making it work reliably in a new border control environment. So let me start with the most fundamental question. Why did we choose face and fingerprint as our true primary biometric? So we choose this combination for very practical reasons. So both are already stored on the traveler documents. So the e-passport chip store the face photo in the data group 2, digit 2, and the fingerprint template in data group 3, digit 3. So the micro carry both as well. So since phase 1 has already cryptographically verified that the chip is linear, so all we need to do in phase 2 is to check whether the left traveler match those numbers. We never need to store biometric data in a separate central server. So this directly satisfies that Malaysia PDP data minimization requirement. For the face recognition, so a camera capture the face, a deep learning model extract the features and we convert it to the digital photo. So for the fingerprint, so we use a ultrasonic scanner instead of the all optical sensor. So ultrasonic work even on the wrong, red or damaged finger. So which is actually the main reason is the Malaysian AutoCAD have high false rejection rates today. For the Mac user, fingerprint matching happen inside the card itself through on-card matching. The raw fingerprint data never leave the chips. As you can see in the table on the right, combining both modalities give us higher accuracy, better spoofing resistance, and redundancy. If one modality has bad reading, then the other can compensate. This slide shows the complete test pattern organized into four layers. Layers one happens before the travelers even reach the gates while they are walking in the queue. Then camera completely capture their walking pattern, their gate, and compare it against a criminal watch list. So if there is a strong match, the immigration officer gets a pre-alert immediately. So layer two is the gate itself. After the first one, authenticates the chips. The face and the fingerprint reference template for the digital and digital are retrieved and ready for the comparisons. Layer three is where we capture the live biometrics. So both face and the fingerprint are captured and before matching, we run liveness detection, also called PAD or presentation attack detection. So to make sure the traveler is a real live person and not someone holding a photo. Therefore, is the decision. The score for the face, fingerprints, and the gate are combined using a vector fusion rules. So only if both liveness check pass and both biometric score exceed their threshold, does the gate open. Any failure sends the traveler for secondary examinations. So this slide shows the UI and the UX design for the traveler facing side of the e-gate, what the traveler sees and does at each step of the verification process. So we have designed it as a four-step sequential flow. Step one is the document scanning. The traveler places their e-passport or my card on the embassy readers at the gate. So the screen displays simple instructions in three languages, but Malaysian, English, and Mandarin Chinese. Once the chip is read and phase one cryptographic verification complete successfully, the screen shows a confirmation, should verify, and advance automatically to the next step. So step two is the face capture. The gate camera is now active, so the screen shows a left camera preview with a face outline guide to help the traveler position themselves correctly. So if the traveler is wearing sunglasses or mask, so the screen display a polite message to remove them. So after capture, the left-hand check runs, so the traveler may be asked to blink or slightly turn their head. So step three is the fingerprint scanning. So the traveler places both index fingers on the ultrasonic pattern. So the screen shows which finger to place and scanning animations. So the left-hand detection runs in a parallel. So checking for switch pulse, the electrical impedance and pressure micro tremor. Once confirmed, the step completes. So the step 4 is the result screen. If all check pass, the screen display verify in the last screen text. So the gate reopens. If any check fails, such as a Lachlan detection failure or biometric mismatch, so the screen shows neutral, please proceed to the counter message, and the traveler is directed to the officer without any alarm or public indication of why. So the front topic is the occluded face recognition. So this is a real and common problem at Malaysian checkpoint. After the COVID, many travelers still wear the medical mask, other wear sunglasses or have heavy makeup, or wear religious head covering like hijab. So standard face recognition breaks down significantly in these situations. So we address this with four solutions. So solution one is the mask data training. So we train the AI model on face image where the mask and glasses have been added. So this teaches the model to work with only the upper face, the forehead, eye area, and nose bridge. So solution two is the region adaptive matching. So when the system detects a mask, it automatically switches them to a mode that only compare the visible part of the face and adjust its decision threshold to match the reduced information available. So solution three is the simpler. So the gate screen politely asks the traveler to remove the sunglasses or the mask. So in three languages. So if someone generally cannot remove them for the medical reasons, so they are redirected to an officer line. So solution 4 uses a time of flight depth camera to capture the 3D shape of the face rather than the texture. So since it reads the facial structures, so not the color or appearance, so having makeup has no effect on the matching. In the last slide, cover two things together: left-node detection and the gate recognition. Starting with the left-node detection, spoofing means that someone tries to trick the biometric sensor using a fake sample by holding a printed photo in front of the camera, playing a video of their phone, or wearing a silicon fingerprint overlay. So these are called presidential attack. So to stop this, we run Linus check on the both modality before any matching happens. So the first liveness, we use three methods. First, a channel response system. The screenshot or random instruction like bring tries and check if the trouble actually does this. So a photo or video cannot respond to a random challenge. Second, RPPG. The camera detect the subtle color change in the skin caused by the blood flow. A fake face has no RP, so it produces no signal. So third, the near infrared and imaging. So let's screen reflect infrared light differently from the printed paper or phone screen. For the fingerprint liveness, we also use three methods. Straightforward analysis check for the microscopic pore and silicon flags don't have. Electrical impedance sensing check that the material on the scanner is actually live tissues. And pressure micro tremor detection check for the natural tiny vibration a live finger produce, which rigid fake product completely flat pressure signal. Both left check must pass before the system proceed to identity matching. So if either fails, the gate block and the official is valid. So now turning into the gate recognition. So this is our merging technology. Cover secondary biometric advance while the camera is still in the queue before they even reach the gates. So dev camera silently capture how the paper works. The deep learning model convert this into the compact gate signature and compare it to the criminal watch list. So this system produces one of the three results: no match, continue normally, soft alert, the official is quietly notified, and hard alert, the gate is closed and the traveler is redirected to the secondary examinations. So the officer make all the final decisions. So only the gate signature is transmitted, then the video is deleted after the 30 seconds. So this complies with the PDPA data minimization requirements. And thank you, that's all from my part.
Hello, my name is Isaac, and today I will be presenting on the system performance and error rate tuning for our automated border control system. To understand the sheer magnitude of our objective, we must first write the data. The ABC system deployed at Malaysia's Johor, Singapore Causeway and Kuala Lumpur International Airport processes up to 50,000 travelers daily during peak periods. KLIA alone manages 32 million passengers annually. Under the ISO standard, we balance system throughput against potential error configurations. At this scale, even a tiny shift in matching error percentages translate directly into hundreds of thousands of citizen delays or, worse, critical security failures. We manage this risk by structuring our systems into distinct operating modes. Our border architecture uses two parallel operating pathways to secure checkpoints. First, we have the primary one-to-one verification mode located at the E-gate. Here, the e-passport is scanned and the live traveler is matched directly against the template stored on the RFID chips. It's incredibly fast, computationally light, and generates high throughput. Second, we run a concurrent one-to-many identification mode across the queue halls. This processes travelers' faces and fingerprints against criminal database watch lists managed by the Royal Malaysia Police and Interpol. Rather than matching one-to-one, it tries to detect watch list targets within a list of top candidates. To fine-tune this architecture, we tried three fundamental metrics. First is the false acceptance rate, or FAR. This measures the probability of mistakenly granting entry to an imposter. Second is the false rejection rate, or FRR, which calculates how often genuine passengers are incorrectly blocked. Finally, we evaluate the equal error rate, or EER. This is the exact point where FAR equals FRR. Biometric security developers use EER as the absolute baseline to judge the accuracy of individual modalities. The lower the EER, the more powerful the biometric technology is. The table on this slide displays the performance of the various modalities. Facial recognition on its own yields an equal error rate of 3.5%. Fingerprint recognition is more accurate with an EER of 1.5%. However, when we implement a multi-modal face and fingerprint fusion, the EER drops to just 0.8%. This is a massive breakthrough. By utilizing score level fusion, we achieve a 4.4 times improvement over facial recognition alone and nearly double the performance of standalone fingerprinting. This fusion is the engine driving our primary gate verification. We do not operate exactly at the equal error rate crossover point because our security tolerance for an imposter entry is near zero. Therefore, we tune the E-gates to an operational threshold where FAR is strictly equal to or less than 0.1%. This configuration gives us an estimated FRR of 2.5%. In real terms, if 10,000 passengers pass through per hour, about 80 will trigger a false rejection and be calmly directed to manual inspection. For the covert watching screening, we tune the threshold differently, utilizing a more permissive 1.0% FAR. This ensures maximum alert sensitivity since flags are simply reviewed visually by immigration officers. The multi-modal fusion curve easily dominates standard modalities across both logometric ROC curves and cumulative match characteristics curve. At our high security gate settings, our fusion system delivers a flawless verification rate of 97.5%. Additionally, in covert identification mode, the watchlist algorithm successfully reaches a rank 1 identification rate of 97.5%. This rating scales up to 99.4% accuracy when officers evaluate the top 5 matching watchlist candidates. In conclusion, our tuned ABC system demonstrates how mathematical modeling transforms operational realities by establishing a layered defense in-depth architecture which satisfies both national security properties and traveler throughput. The combination of strict e-gates and sensitive watchlist screening, supported by quick physical escalation loops, allows us to handle high-traffic hubs with zero operational compromises. Thank you.
Hi, I'm Wei Qi, and I'll be covering Phase 4 Threat Modeling Security Privacy, Phases 1 to 3 Build and Accurate System. Phase 4 makes 8 trustworthy through 3 pillars, which is biometric template protection, PDPA compliance, and officer accountability via AAA audit trail. The core principle here is that the raw template should never be exposed. For my card, on card matching means the fingerprint is matched inside the card's secure element. Only a pass or fail comes out. For e-passport, DG2 and DG3 are only retrieved after Phase 1 PKI verification succeeds. For the gate watch list, cancelable biometrics applies a non-invertible transform. If the key is compromised, just issue a new one and regenerate all templates. Finally, the biometric and identity subsystem are physically separated, sharing only a short-lived session token destroyed after clearance. Figure 7 shows how these 3 mechanisms work together to end-to-end. Next, we evaluated each modality using bioprivacy technology risk rating framework. As shown in Table 2, face, fingerprint, and gate all carry a high overall risk rating. Iris is medium because it requires user cooperation. 3 out of 4 modalities are high risk, meaning active technical controls are mandatory, not just policy. Next, Table 3 applies the full bioprivacy impact framework across 7 dimensions. Risk is higher because use is mandatory and gate screening is converted. We counter this. Storage is on chip only. Raw capture are deleted immediately. Sessions are purged on clearance, and multilingual signage informs travelers before they enter the corridor. This places the system in the middle of the bioprivacy continuum, not fully privacy neutral, but actively controlled. Next, Table 4 maps all 7 PDPA 2010 principles to our system design. Data is collected for border security only. No secondary use. Signage covers notice and choice. On-card matching and PKI bound templates cover security. Gate is purged in 30 seconds and match scores exist only in volatile memories, covering retention. All 7 principles are met by architecture, not just policy. Officers authenticate with smart card past 6-digit PIN, no single-factor login allowed. Access is controlled through 4-level RBAC. Gate operators cannot access session history. Supervisor can override but cannot export the data. Admins manage hardware but have no biometric access. No single role can operate the gate and alter the audit evidence. Every event is recorded in a SHA-256 hash chain log, forwarded in real time to an air-gapped server, retained for 7 years and open to third-party audit. Plus, the next generation Malaysian e-gate addresses 3 failure modes in current auto gates: high FRR, no watchlist identification, and vulnerability to spoofing. Phase 1 verifies the token cryptographically before any biometrics is captured. Phase 2 captures face, fingerprint, and gate with full liveness detection. Phase 3 tunes the system to FRR 0.1 and FRR 2.5%. Phase 4 protects templates, enforces PDPA compliance, and ensures every officer action is auditable. Future work focuses on scaling to Johor CIQ's 300,000 and 400,000 travels per day, and studying biometric template aging in the Malaysian population. That's all from us. Thank you.